Welcome, everyone. I'm excited to kick off today's presentation with the theme of symmetry. Today, we'll explore what symmetry really is, why it matters, and how it appears in various aspects of our world. We'll look at some fascinating examples and understand its significance in design, nature, and science. So, let's get started and discover the beauty and importance of symmetry together. Let's take a look at what's coming up in this section. First, we'll explore what a line of symmetry actually is. Then, we'll see how many lines of symmetry different regular polygons have. After that, we'll move on to translations, which is a slide we're going to cover next. We'll also examine some common math symbols and what they represent. Following that, we'll discuss rotations or turns that shapes can make. Lastly, we'll look at reflections or flips, which are another way shapes can be symmetrical. Throughout this presentation, understanding these concepts will help us see how shapes relate to one another and how symmetry plays a key role in geometry. Let's talk about what a line of symmetry actually is. It's a line on which you can fold a figure, and both sides will match perfectly. Imagine folding a paper shape so that both halves line up exactly. That's what we call symmetry. According to Maryland Content Standard 2E2, we can identify and describe symmetry in different figures or pictures, and some shapes can have up to 4 lines of symmetry. For a shape to have a true line of symmetry, its two halves have to be exactly the same. A great example is when you trace a heart onto a folded piece of paper and then cut it out. When you open it up, you'll see that the two halves are mirror images of each other, making a whole heart. Those two halves are symmetrical because they match perfectly when folded along that line. Now let's look at some flags. Which of these flags have a line of symmetry? The first one, no. The second one, no. This helps us see how symmetry isn't just about shapes, it's also about real-world objects like flags. Recognizing symmetry helps us understand the balance and design in shapes and images around us, which ties back to the overall idea of understanding geometric figures and their properties. So what about these math symbols? Do they have symmetry? Let's take a look. Starting with the plus sign, the plus symbol is symmetric, meaning if you reflect it along its vertical or horizontal axis, it looks the same. The minus sign is similar, also symmetric because flipping it doesn't change its appearance. Now, moving to the multiplication sign, the x, this one is also symmetric. If you flip it along its diagonal, it remains unchanged. These symmetries are more than just visual quirks. They connect to the overall theme of how symmetry appears in different forms, even in something as simple as math symbols. Recognizing these symmetries helps us see patterns and connections that might otherwise go unnoticed. Let's explore the question, how many lines of symmetry do these regular polygons have? Some have just one, like certain triangles, while others, like squares, have 4 lines of symmetry. Notice the pattern here. As the shapes become more complex, the number of symmetry lines can change, but sometimes they follow a clear pattern, which helps us understand their structure better. Now, here's a fun way to think about symmetry beyond shapes. Look at your own name. Some letters are symmetrical, meaning if you draw a line down the middle, the two sides mirror each other. For example, the letters A, H, I, M, O, T, U, V, W, and X are symmetrical. Recognizing these can help you see patterns in letters just like with shapes. In the list of letters, you'll notice some have multiple lines of symmetry, like the letter H with 6, while others like C or S have none. The idea of symmetry is everywhere around us, from polygons to the letters we see every day. And for the other letters, like P, Q, R, S, T, some have partial or no symmetry, which shows how diverse symmetry can be. Interestingly, some shapes and letters can have an infinite number of lines of symmetry, like a circle, which has an endless number of ways you can split it and still get mirror images. So, whether we're talking about geometric shapes or letters, symmetry helps us understand the balance and structure in the world around us. It's a fascinating concept that connects geometry to everyday objects and even our own names. Let's take a look at the concept of rotation, which is also known as turn. Essentially, it involves turning a figure around a specific point or a vertex. Imagine spinning a shape around a fixed spot. That's exactly what rotation is. Now, if you click on the triangle, you'll see a visual demonstration of this action. When we rotate a figure, we're turning it around that chosen point or vertex, but the shape itself doesn't change. Only its position does. Understanding rotation helps us grasp how shapes move and transform, which is fundamental in geometry. It's a key concept that connects to many other transformations we've discussed. So remember, rotation is all about turning a figure around a point. Think of it as a spin or a turn in space. Let's take a closer look at the concept of translation. As you can see, translation is essentially the action of sliding a figure in any direction. When we talk about this, it means moving a shape without changing its size, shape, or orientation, just shifting it from one place to another. If you want to see this in action, simply click the octagon on the slide, and you'll observe how the figure slides across the plane. The key idea here is that translation involves movement without distortion. It's all about repositioning. This concept is fundamental because it helps us understand how shapes can be moved around in space, which ties into the larger theme of geometric transformations we've been exploring. Whether in design, art, or even real-world applications like navigation, understanding translation is really about grasping how objects can be repositioned easily and accurately. Now let's take a moment to look at reflection, which is the result of a figure flipped over a line. If you click on this trapezoid, you'll see the reflection in action. It's essentially like holding a mirror up to the shape, creating a mirror image across a line. As we examine different shapes, try to figure out whether each one shows reflection, translation, or rotation. Reflection, as we just discussed, involves flipping. Translation is when a shape moves without changing its orientation, sliding straight across. Rotation, on the other hand, is when a shape spins around a point. These concepts are fundamental because they help us understand how shapes can move and change in different ways. Recognizing whether a shape has undergone a reflection, translation, or rotation helps us analyze and describe movements in both math and real-world applications. Remember, the key is to observe how the shape's position or orientation changes relative to a line or a point.